Thank you, Marissa. Hi, hello, everybody. Good morning, good afternoon. And my name is Honghai Li. I work for Coastal Hydraulic Lab. And today I'm going to present a case study. So in that study, we use the coastal modeling system developed by CIRP program and to do sediment transport and for dredging material placed at placement site near Beaufort Inlet, North Carolina. For the study, team member had Li Lin at CHL, and Carter Rucker and Kevin Connor at Wilmington District. Some background information, and you see here the figure show the study site. So Beaufort Inlet is south of Beaufort township of Beaufort, and so there's a maintain a navigation channel and has a dredge depth 45 feet, and the wearing width and then from 450 to 800. At harbor, it's a little bit wider, it's 1350 feet. The channel is pretty long here, so it's extended to the open ocean and connected to the Morehead City Harbor and also Atlantic Intracoastal Waterway here. Objective and for the area, there's a dredge window for the area. Usually it's between December to April every year. And the district like to explore the year-around dredging and placement to raise the efficiency of the dredging placement operation. You can see here the dredging material is placement at 3 sites. So 2 nearshore sites, Shackpole Banks, and the second one is Booger Banks. So both are a nearshore placement site. So the other one is an offshore site, ODMDS. And you see the channel, and it's all the way from open ocean into the harbor area. And for the placement material to evaluate the transport, and we apply this model and to simulate the sediment plume. So originated from these three placement sites. So modeling approach, and we use a coastal modeling system. You see that's a grid we developed for the study, and the model has a variable resolution telescoping grid. And the forcing for the model, usually we have water level, wind stress, and a wave spectrum. And also here we use the sediment mapping feature in CMS to track the sediment plume. So place at these 3 sites separately. And some people ask how do you simulate, use the sediment mapping to simulate the sediment transport, like kind of a tracer, sediment tracer. And in CMS, we have a transport equation like show here. and the K is the sediment grain size. So usually, a lot of the time we run single grain size sediment transport. So if you run multiple grain size, so each grain size will use this equation to calculate the transport. And for the sediment we are going to trace, we just specify one of the grain size. So by calculation, by get output, we can see how the behavior of those kind of sediment move in the system. So for the simulation period, we choose is the summer and winter months, two months. We want to see, because the dredging window is usually winter, springtime. So we like to check the summertime, so different season, see if they are behaving differently. And the table shows the physical setup for this placement site. So we have 1, 2, 3 Shakeful Bank, Boga Bank, and ODMDS, Ocean Dredge Material Placement Site. And you see the average depth for these 3 sites is a little bit different. Nearshore site, average depth is around 7 meters, and the offshore side is double, it's 50 meters. So it's in the relatively deeper area. And the area size is 5 nearshore, 8 and offshore, a little bit bigger. And also material we placed is around 500,000 and cubic yard. And first, what we did, we collect some wind data, wave data between 2016 and 2021. So we pick a representative year for those 2 months. And then we see the seasonal change for the wind and wave condition. And the wind data we get from this at Cape Lookout, North Carolina, CLK7, that's the NOAA station. And the left-hand side of this figure is the summer wind rolls, and the right-hand side is the winter. So you see, in terms of wind, there's 2 distinct wind pattern here. And the summertime mostly southwest, wintertime is northeast. And also we have some wave data. This is also CD buoy, and then it's offshore of a Beaufort site. You see the location is here, and the wave looks very similar in terms of direction. So mostly from south, because the bay open to the south, and the amplitude, wave height is a little bit different. So you see winter months, the wave height is there's a lot of extreme event, right? You have a much bigger wave height compared to summertime. And then we have we did a model simulation, and we got a wave and current analysis here. And this is the average, monthly average wave height. And this is August, and the bottom one is December. So it's in terms of a monthly mean, and they have a similar direction, and a little bit stronger wave height during winter time. You see the average we check offshore. It's summertime. Its average is 0.85. So the winter time is larger than one meter. And near shore, and also winter is a little bit large. And inside the bay, in the sun, boulder and back sound. So inside, so the wave is pretty small. And then we check the current condition. And first we see we pick the flood tide, flood current and ebb current. So the top one is flood current. So you see the flow goes in, and the bottom one is ebb current. And then if you check the legend, is a pretty strong current. So the legend here is 1.5 meter. So the wave, the current is for the summertime is 1.2 to 1.4 meter, and the winter time is a little bit smaller. And the reason is during the summertime we pick a month. So early on during this tidal period, there's a hurricane Isaac passing the area. So that's why it's corresponding to a little bit stronger current during summertime. So early summer, like August 4 and 5. Yeah. And also there's a feature here, and you see if you check the flood current, so once the flow into the sound area, there's a two branch of current. One goes to east, one goes to west. So that's the strong current. So this will help us understand the sediment plume movement too. And then we have a monthly average current and here. So you see the scale is only 0.5 compared to the flood and ebb current. But you see the mostly is a flood dominant kind of thing, right? So the mean flow, monthly flow goes into the sound, goes into the bay from outside. And also you see basically two branches of a current. One goes to east on the east side of the inlet, one on the west side of the inlet. So now we go to the sediment transport. For sediment simulation, we specify the site, the placement site as a sediment source, right? We leave the sediment there, see where it goes, and we also define some area, like the 10 area around the inlet, like a 2 area, like a 9 and 10 is a nearshore open ocean area. So 7, 8 is offshore, is also along the channel. And 3, 4, 5, 6, the area inside the sound. And 1 and 2 is near river marshland area. And when we run the model, we see how much material moving into certain area. So we have some sense how the plume move, and after release placement at the site. Okay, here is the summer result. So the plume show is every 5 days. Because we run 30-day here. So every 5-day simulation, you see the initial plume is go along shore and go east to west, and then some move into the sound area, the bay area. And then as time goes by, it's outside it didn't change much. And but inside also move very slowly, and then the intrusion goes to inside the bay. Also, you see the more material move to east, right? Get into the bay, move to east, right? That's because that's current split into the bay. And then we compare with the winter condition here. And the winter also 30-day simulation and 5-day interval. And when we compare initially, as I mentioned, summertime, the first 5 days we have a hurricane. So that's why you see the summer expansion of the plume much faster than the winter time. But because winter storm is stronger, totally, I mean monthly. But at the end of a simulation, day 30, you see the plume is very, I mean, outside, it's very similar compared to summer and winter. So this is the first placement site. So the second placement site is on the other side of you see this figure, and it's very similar to the first one, but it's go along shore and across shore, and when it's moved to the sun, it's along the on the west side of the inlet. So it's bring by the other branch of the current, so into the inlet. And yeah, you see at the end of the simulation, it's spread a lot compared to the first one, right, to the west side. And then again, we have a winter time. So at the end of a simulation, you see very similar pattern, right? And in terms of the range of spreading and how far is go to the bayside. The third one, we see the offshore one. The offshore one, so we see the average current at the offshore side basically is less than 0.1 meter per second. It's less than 10 centimeters per second. So the advection here is relatively weak, and so mostly, so the expansion I think caused by the storm-driven diffusion maybe, right? So you see at the end of the month, so all the plume basically is outside and within like 800-meter range. Yeah, it didn't go beyond that. Yeah. And then I put the mass got into each area, see how much mass move into still in the offshore area, and how much go into the bay, and which side it will go. And here is a summer case and a winter case. And so don't see the number is too big, but you see the percentage, like this one, the summer case, you see the material move near shore is 0.7%. And 0.7% compared to the other number is a relatively big number, right? Released from this side. And then 3% moving into the channel area. And then relatively small number goes to inside the sun. But on the east side, west side, the percentage is very small, very small. Yeah. And compared to the winter case on this side, so the material moved to onshore is a little bit more. It's 1%. So compared to the summer case, it's 1%. And inside again, only at the entrance has some material, a significant amount of material, but at the other side is also small, and also some 3% similar to summer case moving into the channel here. And for the Google Bank, so you see the offshore here corresponding to this placement site. There's 1% moving onshore because on longshore cross-shore transport, and 6% moving to the channel. So it's much more than this site release. Yeah, this Google site compared to Shackleford Bank. So there's more material moving toward the channel and also into the sun, right? So you see even here there's a 0.04%, right? And also winter case, you have 8% moving to the channel here, and also 1% moving onshore. So for the offshore side, so most material stay and near the placement area, and really there's a small amount of material moving to the offshore channel area. Yeah, not much. I mean, there's zero moving into the sound area. Yeah, so I draw two figures. One is these two are nearshore site. So you see the mostly caused by the advection, like tidal current, is these two nearshore site. And small area represent kind of a diffusion by the stir by the storm condition. Yeah. So we see through this study, and then so the nearshore site is under influence of a coastal process, and so it's due to the wave-driven longshore cross-shore transport, and so the material moving into the bay mostly by the tidal advection. Yeah. So storm condition, tropical storm, extratropical storm have a major impact on the sediment plume. We see the plume, so you can see the westward expansion of a sediment plume in Bourgeois Sound, and also that's during summertime, right? And also for the offshore side, you see during the wintertime a relatively large east-west plume group, right? So that's also corresponding to winter storm, and current so in the deep area is relatively weak, and so the movement of a sediment plume is limited, and due to weak advection. Yeah. I guess that's it. So any question?